All right, so homework, everybody submitted. Okay, cool. Um, so we should look at the solution. All right. And what I have here is the solution that actually produces the entire explanation of the solution, right? Which is what I have posted. So if you look at this, essentially output, right? It generates that automatically, right? So let's try to strip it down to what you should have submitted. Okay, so I'm going to define a helper, right? Because I want the solution to be, I want this extra argument L here, or I want the H, whichever, but actually the L is the extra argument. And this will help me explain the solution easier, right? So let's say I have a certain distance, right, to cover, and let's say I'm already in the middle. So I'm already somewhere here, right? And I'm going to copy this. So this is L, right? And this is H. And L plus H is always equal to the original D that we want here, right? So now, let's say I already made it to this point, and I'm on the path of the shortest. Let's just assume that I'm on the path that gives me the shortest number of jumps, right? I have two choices. I can jump forward according to L, right? So I can jump ahead L divided by 2 plus 1. So let's say I would jump somewhere here, right? L divided by 2 plus 1, right? Actually, I would jump here, right? So this here would be L divided by 2 plus 1. And to avoid all these colors, let's make everything a comment, right? Or I could jump somewhere here, and I'm going to assume that this is H divided by 2 plus 1, right? So this part is H divided by 2 plus 1. Is this clear? Is this clear? Right? So what can I do now? Going from here forward, I can see what's the minimal number of jumps from here to here. And going from here forward, I can see what's the minimum number of jumps from here to here, right? And then of these two, I can choose the minimum. Each of these, each time when I go from here to here, this contributes by 1 jump, right? Or I go from here to here, this contributes by 1 jump. In both cases, right? So it's about the remaining distance, right? It's about the remaining distance. Which one will give me the minimum number of jumps from that point on? Okay? So let's keep deleting the explanation. So let this be an L plus 1. And let this be an H plus 1. Right, and when we do that, actually instead of having 1 here, I can have one here. All right. Am I missing something? Do I have an extra bracket or something? Not exactly sure why this is has a different color. All right. So L plus H is always equal to D. So in fact, I could get rid of L, right? Because I could compute L as D minus H, but it makes it easier to compute, right? So L is what I have to the left, H is what I have to the right. So assuming that I make a jump right now, right? My choice is either to jump L divided by 2 plus 1 or H divided plus 1, right? So I have to see what's next. What's the minimum number between these two? I have to compute the number of jumps, the minimum number of jumps from here, and the minimum number of jumps from here, right? So we're going to make the following assumption. Helper computes the minimum number of jumps when I have already gone a distance of L and I have a remaining distance of H, right? I'm going to make that assumption. So under that assumption, whenever I have taken away L divided by 2, the minimum number is going to be the recursive call helper applied to what's now at the left. It's this quantity, right? And what's now at the right? It's this quantity, right? So this is what this represents. So I have this. So to the left I have this. And to the right I have this, right? The other possibility is to jump H divided by 2 plus 1. This H, let it not confuse you. This H is this, right? This is H. Remember that, right? So the other possibility is to jump this much. And I want to know the minimum number of jumps for this distance, right? So this is helper, and this is what I have at the left, and this is what I have at the right. See, this is at the left, and this is at the right. Now I have these two numbers. What I have to get is the minimum number of the two numbers, the minimum of the two, sorry. Okay, and then either I do it this way, either I go this way, or I go this way. It's still one jump, right? So I'm going to add 1 here. And this is the number that we can return. Obviously, we need base cases. So if H is 0, it means that I have reached my destination. So if I am at my destination, the number of jumps to my destination is 0, right? If I overshoot the destination, I have to return something that would prevent that number to come into the computation, right? I have to find something clever. And because these numbers are mixed inside a minimum, right? The largest possible number that can be represented in Python would be a good choice, because at least one of the choices will be 0, right? There's always a solution. At least one of the choices will be 0. So that very large number, when mixed with 0, we will get out of this minimum, we will get 0, right? Now, if you didn't know this, so this is something you learn now, this is the largest number representable in the system. But if you didn't know this, you can just put some very large number, right? So if you've done that, you did good. Okay? Where do I start with 2 brackets? I didn't see the second bracket. Good, very good. Yeah. Okay, so wonderful. And then what do we return? What these jumps needs to do is to start from 0, right, and have a remaining distance of d. All right. The important thing is to understand the pattern, right? Minimum is not very different from plus and star. Minimum is commutative and associative. If I change the order of the arguments, I still get the same result, right? And minimum of A and min of B and C is the same as, right? So if I write something like min of A and min of B, C, that's the same as min of A, B, and C, right? So that's associated, which means that pretty much Fibonacci should work. It should work in a similar way. I mean, in Fibonacci we use plus, here we use min, right? We should have pretty much the same kind of reasoning. All right? So try to understand the pattern here. Okay? So this is what produces the result. No? No what accumulated? Right, but I don't give an accumulator in Fibonacci either. Right? So remember, Fibonacci is, so let's define Fibonacci again. Of n is less than equal to 1, return n, else return fib of n minus 1 plus fib of n minus 2, right? So there's no accumulator. If you look at the towers of Hanoi, there's no accumulator either. All right? So for practice, since we now know lists, let's write the towers of Hanoi, but where the solution is not obtained by printing, but rather by returning a list. Okay? So Hanoi, right? And remember, there we had number of disks, and we had the origin pole, the auxiliary pole, and the destination pole, right? If n is equal to 0, is that equals? Equals to 0, I'm going to return how many moves do we need from, if I have to move 0 disks, how many moves do I need to make? 0, right? So I'm going to return the empty list of moves. Else, okay, so remember how we were, what we were doing there. We would solve the problem for n minus 1 going from A to B using C as an intermediate, right? So I would use Hanoi, and I would move n minus 1 disks, and I would go from A, right, to B, and then the only one left as an intermediate is C, right? And then I have to move the largest disk from A to C, very good. So now I'm also introducing you to what a pair is, what a tuple is. This is a tuple of two elements. Let's put it closer to the middle of the screen. Okay, A to C. So what you see inside here is a pair. Maybe we don't need a pair. Let's make it a list. Okay, so we need to return a move. It has two elements. I cannot return two elements unless I aggregate them, right? So this becomes a list of lists. Or it can be a tuple of lists, or it can be a set of lists. A set of lists is not good because it doesn't have order. So we're moving here from A to C, right? That's what we're saying. Then what we do, we move n minus 1 disks from, where are they? They're at B. And where do we want to move them? To C. And then what's left as an intermediate is A, right? Okay? So this is the solution for, let's run this. So I'm going to take this into, I'm not going to use idle anymore because it's really, even though it's running there. I thought I opened, I didn't get there yet. I'm not in idle. So another thing is that this, I'm also using the wrong editor. So Python doesn't like tabs and spaces being mixed. All right, so in this process, we're going to learn something new. So let me enlarge this a little bit. Minus I test.py. Else and else might need a column. So what we do now is we read a file and then we continue running, right? And it's as if we typed all those commands, right? So Hanoi is now defined, right? So now we can run Hanoi, let's say a 3, and we say that our poles are 1, 2, and 3, and then non-type. Which one is non-type? Oh, this is the empty list, right? Yes. Yes. So where do you get? So have n minus 1. One moment, let's debug this. in auto indentation level again. Zero to 1, 3. I can't understand where the non type is coming from. Alright, let's break it down. Now there's a place where I can stop using tabs. So, oh, I think I forgot to say return. Should have called me out for that. Here we have to say return. Okay. All right. So notice the solution. What I should also do is get rid of the debug line. So Control S, going back, Control D. Right. So notice the solution. Right. Instead of printing, we are returning a list of moves. Right. So the first move is 1 to 3. The next move is 1 to 2. The next move is 3 to 2, and so on. Right. And now there's a plus sign there, right? But it's between lists. But which means concatenation. But guess what? This plus sign is also associative, right? It's not commutative, but it is associative. Actually, commutativity is not that important. Associativity is important in that context. And in this case, again, we are using the same pattern, right? So it's like this is the 1, the plus 1. Right? Previously we had essentially helper of something. We had min of helper of something plus 1, right? That was the homework. So notice that this expression is not that different. So this is very similar to the plus 1. And these two guys are inside the minimum, are as if they were inside the minimum, right? So it's an expression between two recursive calls. The same pattern. It's the same pattern of reasoning. Okay? So try to think about that. Hanoi, the problem that I had for the homework, Fibonacci, they're very similar in the pattern of reasoning. and try to extract that as a pattern of programming. Okay? Just think about it. Right, recursion is gone. You're not going to see any more homework on recursion, but for your future as potential coders. Well, I mean, why do you mean it's difficult? It's not difficult. It's To me, it's not difficult, right? To you, it's difficult because you're seeing it for the first time. So if you think about it for a few more days, then you're going to get there, right? So it's an expression that has two recursive calls inside. Okay. Yeah. Well. So here you have two operators, and you have two recursive calls, right? Here you have two operators. Well, the plus is here, right? And you have two recursive calls. Okay? Okay. Questions? Yeah. So essentially, the solution that I was hoping to get was essentially this, right? So you can obviously make it even shorter because you can put the helper, you can put it inside here, and the second helper you can put it inside here, and 3 lines are compressed into one. And okay. But okay. Questions? How do I use J0? What do you mean J0? Line 31. No, so ignore this. This is what, oh no, I'm still in this. You see, I wanted to give you some, the possibility to verify your results, right? So obviously I didn't write this by hand, right? So that piece of code that is here generates those lines. Oh, well, so are we done with this? Can we return back to the original form? Okay. Let's see if we're... All right. So you don't want to return just the counter, right? You want to return also the history of jumps. How much did you jump at each point and what was the position, right? So we're going to use a list that accumulates the history. All right. So, and that's why I expanded it so long, because, right, I want to return the number of jumps, but I also want to accumulate the history, right? So this is the, and how, because I have two things to return, I can't return just a number, right? I have to return an aggregate. And I chose to return a tuple, which is, right, what we're going to learn about today. They're not very different from lists, just that we put them in round brackets instead of square brackets, right? And then, because I have a tuple, right, when I want to print the result, I have to print the first component of the tuple. There's two elements in that tuple. So J0 is going to be the first component, and then J1 is going to be the second component, which is the entire history. So I'm going to print the result, which is what you see here, right, like this. And then I'm going to print this entire sequence. So for that, I need another for loop. Okay, so for this, I need another for loop that prints the entire the entire history, right? And I want to give you results for a reasonably large set. So I chose to do it from 0 to 64. From 1 to 65, actually, yeah. So I want to do it to have 64 values. Not to 65, to 64, 1 to 64. So this is exclusive. Okay? So that's gonna be another technique. So you need to return more than one thing, then you aggregate. So when you aggregate, you have to think tuple, list, set, something. Okay? So if you want to obtain the original, just go to all these round brackets and delete the second component, right? So that's what I did to get the version. Delete this, and obviously the corresponding bracket, delete this. And from here, right, delete. So notice that I'm getting the minimum between two pairs, two tuples, right? So you have to delete this one, and you also have to delete this one. And then you're going to get the version that doesn't give you back the history. I'm going to make this available to you. Okay? So you can try to understand it better. Good? Okay, cool. So, how about the sieve? Are we good with the sieve? The sieve. Do you know what a sieve is? Right? So, it was used by gold miners to try to separate the sand from little stones, little nuggets of, that might have gold inside. And it's used to separate impurities from flour, right? In the kitchen. Okay, everybody knows what a sieve is. So the story is that Eratosthenes, who's the guy who invented the sieve, did the following thing. He took a piece of a skin, a cow skin, and he wrote the numbers from 1 to 100 on them, right? And then he started to punch a hole on every non-prime. So he started with figure that 2 was a prime, and then started to punch a hole in all numbers from 2 to 2. Every second number he punched a hole in it, right? And then if a hole is there, it doesn't matter if you try to punch another hole in it; it's still a hole, right? So that's one interesting property. So he went to 3 then, and he punched a hole on every third number, even though some of them were already had holes in them, right? And then 4 wasn't available anymore, right? So then you move to 5, and then every 5th number, and so on and so forth, right? And figure out that all these were primes. And this method of finding out primes is called the sieve of Eratosthenes. All right. So this is pretty much what we're trying to do in this piece of code. The left ones, the ones that are left, are primes. Yes. You didn't know the story? Your math teacher didn't tell it you? Good. You learned something from me. And then again? Of course there will be. 2, 3, 5 will be left. Where was the... So if you write, I'm just going to write from 1 to 10. 1, 2, without 1. Start with 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So now I'm going to switch to... I should be able to switch to insert mode. I'm not sure how. So from 2, I start deleting every second one, but I'm going to put an X on it, right? And then X, and then X. That's the whole 1, 10, right? X. And then 3. I'm going to move on to 3, right? And every third number. This one already has a hole in it, so I leave it as is. This one X, right? So then I'm going to move to 5, and every 5th number, right? So 2, 3, 5 are left now. They're not. We won't be able to put a hole in it. Is this clear? That's how it works. Oh, go to Wikipedia and check. It's not the fastest way to have the sieve of Eratosthenes, but I think it's the one that is probably easiest to understand with what you know so far. Okay? All right. So we're going to talk a bit before we go into tuples, which are very similar to lists, just that they're not modifiable. We want to talk about a few advanced features of Python, which I think we have everything we need to understand. Okay, so there's often this need to use a function without knowing its number of arguments. Okay, and we actually have functions that take a variable number of arguments. For instance, print. Okay, so print. If I say 2 and 3, it works, right? Print of 2, 3, 4 works as well, right? So it has a variable number of arguments. It's the same with min, right? And min of 2, 3, 4, 5, it works as well, right? And I should randomize them a little bit, so it's not always the first one, but you know what it does, right? The important thing is, so now, but if I say min of 2, 3, 4, what do you think I get? 2, 3, 4, right? Oh, still 2. Yes, because it works. Min is not a good example. Yeah, so 3, 4, 5, and it's going to give you 2, 3, 4. Okay, so it works fine. What's a good example here? Okay, let me create my own function. I'm going to take this function that takes 2 arguments and adds them together. All right. So now, if I say f applied to a and b, 2 and 3, it works fine, right? It won't work well for 2, 3, 4. All right. And then it will not work well for a tuple. Let's not use tuples. Let's use arrays. For the same reason, right? Because it takes only 1 argument. Okay. So now let's say I have a list of lists. And then 3 and 4, right? And 4 and 5. Okay. So this is a list. And I would like to add all inside, right? I would like to do 2 plus 3. I would like to do 3 plus 4. And I would like to do 4 plus 5. I would like in the end to return 5, 7, and 9, right? This is what I would like to do. So I have the function map, right? Remember map? And I could do that very easily by saying sum, and let me make this list into, give it a name. All right. So then I can say map sum and L, and I could get the list here. Okay. But let's say sum doesn't exist, and all I have is F. All right. All I have is F. So if I apply F here, this is not going to work, right? Why? Because what gets computed is F applied to list 1, 2, and list, sorry, and then I have F applied to list 1, sorry, I made the list 2 and 3. Then the next one would be F applied to list 3, 4, right? And each invocation is wrong. Is this clear? So this is what map would compute, would try to compute. But when you attempt to do f applied to 2 and 3 as a list, right, which we have tried already here, right, this will bomb. Is that clear? So we can do f applied to 2, 3, the second, but we can't do this. Yes. Well, some as men is able to. Well, we're going to get there, right? Just give me 10 minutes. In 10 minutes, we're going to be there. So the question is now: can I turn the 2, 3 as a list into 2, 3 as separate arguments? No. Is this clear what I'm trying to do? I'm trying to take the tuple or the list and make it into separate arguments. Disaggregate them, yes. But one at one go, not individually by extracting the 0th element and the first element and whatever. Is this clear? No. So there's a standard feature. All right. So I'm going to say map, and I'm going to say lambda t, which is a list. Make it sequence, right? Lambda s, and I'm going to say f applied to star s. Okay. So this star s, this star that we put in front, will convert the list into separate arguments, right? So to make it more clear, if I say this, let me copy this one. No. Wrong. So if I execute this, I will get the correct result. Is it clear what's happening here? Yes. What do you mean output? A equals star, that will make no sense. That's not valid. So you want A equals star, right? And then you want, oh, that will not work either. Right, it's syntax error. So the star is not an operator, it's a notation. All right? It doesn't have, in this case, it doesn't have a standalone meaning. So when you're opening the bracket for the argument and say star inside, it will take whatever aggregator, whatever iterator is there, and dismantle and disaggregate it, as you say, right? And turn it into separate arguments. All, everything, anything. No, just one level. This is why this works, right? This is why, where is it? This is why this works. Otherwise, if it had, because S is a list of lists. No, you can't. It's a syntax error. So star is not an operator. When you're saying, can I put 2 stars? You're thinking of star as an operator. It's a notation. Okay. So now, can I do the opposite? Let's say I have a function that only takes lists. So there is such a function, I think. Reverse or sorted. Yes. So if I say 1, 2, 3, it doesn't work, right? sorted of, let's not put them in sorted order. Let it do some work, right? This works, okay? So now I want a function S that sorts. I would like to have a sub-function called S, so I can say 3, 2, 4, 1, and I would get the list of sorted arguments, okay? So we can use the arrow in the opposite direction, right? So I can say here, star list, okay? And I can say return sorted L, okay? L is my argument, is L here, right? Which is going to be 1, 2, 3, yeah. So now if I say S 4, 2, 3, 1, I'm going to get the list of 1, 2, 3, 4. Okay? So do you... So makes internally 4, 2, 3, 1. It is the star notation that automatically makes that, performs that conversion, right? So when it gets to this point, L is already a list. Actually, when it gets to L is a list, right? Star L is 1, 2, 3, 4, but L is a list. L is the list 1, 2, 3, 4. Sorry, 4, 2, 3, 1. Okay. So that's in general an important conversion to understand. It's kind of an advanced feature of Python. It will help you understand the video that I have uploaded already. So at this point, you're prepared to watch the higher order programming video. Should you choose to? It's not compulsory, and you get that information. So the interesting thing now is that you see sum and min work with any kind of combination, right? So you can say sum of 1, 2, 3, 4, and you, no? Well, min of 2, 3, 4, and you get a result. You can say min of star 2, 3, 4, and you get a result, right? So it doesn't quite matter how, right? So it gives you the ability to write functions like this at this point. In which one here? This one I didn't put any. Where did I put a star here? Yeah, I didn't. But whoever defined min put, right? Yeah. So now I can define my min, right? To be and I always take a list here. Okay, and then I can do the following things, right? I can say if L len of L equals 1, right, and type of L0 equals I'm not quite sure here, so this I would have to Google, but I'm going to say iterator, right? It's something iterable. Then I can assume that this guy is a list, right? We're in this case. Otherwise, if this is false, if this condition is false, I'm going to be in this case, right? And I can return a result in each of the cases, right? So I can write functions that are very flexible in terms of the arguments they accept. Does it make sense? Mm-hmm. here. I'm not quite understand what asterisk performs. So I have two ways. I have a different way of calling this function, right? So sorted needs a list inside, right? S doesn't need a list inside, right? So I want to take advantage of the existing sorted, but I would like my syntax to be more elegant. All right. So I write a new function that performs a conversion on the fly. Takes 3241, makes them into a list, and gives it to sorted, which sorted can only accept lists, and then sorted gives me back, all right, a sorted result. Okay, where is this extremely useful? It's extremely useful in cases where, for instance, there's already a piece of code that has been written, and you just want to replace a small part, or even more, right? You just want to pass in a small part that performs some computation that suits you, right? And then the only way that computation, that function can be provided by you is if it takes arguments without the arguments being into a list. But what you have is the list, right? So then it helps you to perform a conversion on the fly. Okay. Now, a neat trick. So we already have a function called zip. Okay, let's talk about tuples, and then I'm going to show you a neat trick that uses this. All right. So tuples, as opposed to lists, are immutable. So what were we able to do before? We were able to do, and if we go back here, I have a list called L, and I can say L index 1 is the string ABC, and then L has become, we've changed that, right? So a tuple will have brackets, round brackets around, something like this, right? So I can say T equals, and if I try to say T1 assigned ABC, for instance, that doesn't work anymore, right? T is still 1, 2, 3, right? I can still access T1, right? I can read, but I cannot write. I can't write. And that's very useful sometimes. Okay? So everything you know from lists still works except for things that mutate the list, right? We don't have append, we don't have expand anymore, right? So in many ways, it is simpler. Okay? Oh, reversed was the. We haven't. I'm not sure whether we looked at the reversed. And this always has to be turned into a list or a tuple. So now we know about tuple, so you can see tuple here, right? I don't think I covered it last time. So it works for list as well. So reversed is very good because it creates a completely new object, right? So then it works for tuples. It won't work for sets, which do not have word. All right. So concatenation, multiplication works both ways. Comparison, right? All comparisons work exactly in the same way as for lists. Now, the tricky thing is that if we use round brackets, and round brackets have too many meanings, right? The other use of brackets is to to settle the order of evaluating operators, right? So you can write something like 1 plus 2 times 3, and that tells you that 1 plus 2 is supposed to be performed before, right? Also, brackets are used for function invocation, right? So if I say sign, I would put brackets here to use to have function invocation, right? So the question is, if I want a tuple of one element, obviously I have a tuple of a list of one element, right? If I want a tuple of one element, what should I do? And this is just an arithmetic expression, so it cannot be a tuple, right? So we have to make a choice. What does round brackets around the number mean? And should it mean the tuple of one element or the expression denoted by that one element, right? And what that happens in most programming languages is that it represents the expression. So how do we create the tuple of one element? And the solution given by Python is to have a comma inside, and that tells you that it is. When it is printed out, that comma is still there to make you aware of the fact that it is a tuple. Now, because of this, the comma can be used at the end of any sequence, right? So 2, 3, and it is legal to leave it there, right? Though it doesn't mean anything. So at the point when you have multiple objects inside the tuple, it is clear that it's a tuple. So then the spurious comma at the end, Python doesn't print it anymore, right? It works for list as well, right? So the comma at the end is not an error. 2 commas, however, will be an error, right? So just for uniformity, because it works for 1, it works for any number of elements. So remember that. All right. We can convert any iterator into a tuple. All right. Remember that this conversion is not for free. So often you think, oh yeah, well now I'm going to use a set because I want uniqueness, and then at some point I'm going to convert into a tuple. So because it's just one operation, it takes a number of it takes a time that is proportional to the length of or the size of the set or of the list, whatever, right? So these conversions don't come for free. All right, and now let me show you the trick. So the typical way of representing matrices is as a tuple of tuples, right? So I'm going to have the matrix 1, 2, 3 on the first line, and then 4, 5, 6 on the second line, and then 7, 8, 9 on the third line. Okay? So it's a tuple of tuples. M is a tuple of tuples. So now we want to transpose this. Okay? So we have a function called zip. Do you remember it? Have we talked about it? We haven't? Oh, sacrilege. Oh yes, we haven't, I think, because it uses tuples. I also need to see this. Let's make it a list though. Right? So zip creates pairs from multiple iterators. Okay? And you're going to wonder what happens if one is longer than the other. Right? It stops at the shortest. So what does it do is it takes the 1 from here and the 4 from here and creates a pair. Okay? Then it takes the 2 from here and the 5 from here and creates another pair. Is it clear? And it can. What would be different? Because a list takes a lot more memory than an iterator typically. So what you want to always give back is an iterator if possible, right? The exception is sorted, as you might have seen, because sorted we'll talk about iterators, and you'll see how iterators on one, they don't take as much memory, they take much less. They only look at one element at one time. And then they can be infinite. Okay? Clear? So we want to transpose the matrix. What's a cool way to do that? Think about a star. So remember, T is the tuple, right? Or M is the matrix, sorry, M. And the bloody list. Okay? This is a really cool thing. The star made a huge difference. Is it clear why it works? Okay, so if I would take zip and this, and the list, it's clear that it works, right? But what I have in M is this, right? So then, to make it work, I put a star in front. This will work too, right? So now you're going to say, oh, well, what's the big deal? Just delete the bracket. But I want to remind you that what I have, and let's say this comes from the outside and it's not within my control, is M. That's what somebody gives me. They give me M, the matrix. It's an object. All right? And say transpose it for me and give it back to me. Okay? I see extreme puzzlement on some people's faces. It zips numbers together, right? So if you look here, this was the case. This was what explained it. Or let's take this one. It takes the first element from the first list and the first element from the second list, creates a pair. Right? 1 and 4, I get 1, 4. Then the second element from the first list and the second element from the second list, and I get another pair. Then the third element from the first list and the third element from the second list, and I get another pair. Right? So, okay, so let's take another interesting example here. Let's say I have two lists. And somebody gives them to me, and you look at them and say, oh, it's 3 numbers in your list. No, let's say somebody gives you a 1 billion element number, a list. Okay? Which is nowadays very, not that much. Right? So I have L1 equals my list 1, 2, 3. And then I have the list L2, which is another list of numbers 10, 20, 30. Right? So these two lists are given to me by somebody else. They are very large. I can't go and edit them in a text editor. I can't even load the text in a text editor, right? And now they say, oh, well, add the numbers rank by rank. So add 1 plus 10, 1 plus 10, 2 plus 20, 3 plus 30, and go on 1 billion times. Keep going, right? How do we do that? So I will need zip, right? So I will need zip. So one way to do that is map, okay? And I'm going to use the sum, and I'm going to need to use zip of L1, L2, right? And the list. Because otherwise I can't see what's inside. Okay? But now let's say that instead of sum, which works very nice with an iterator, right? Let's say I want to do first element or second element to the power of the first. First element to the power of the second is not going to be. Let's say I want to do something like that, right? How would we do that? Exactly. Very good. So I'm going to have a lambda here. And I'm going to have something. And then I'm going to have zip of L1 or L2. Okay? And the question is, what do I put here? So definitely I'm going to have 2 arguments. What am I going to have? X and Y? What do you going to have here? I'm proposing X and Y. Do you have a strong reason why you would object that? Are you objecting to the use of the letters? Should I call them A and B, or are you objecting to the fact that there's 2 of them?
Oh, I'm not joking at all.
No, I didn't say joking. Are you objecting?
No, I'm not.
Oh, you're not objecting.
Yeah.
Right? So if I have 2 arguments, I would put X and Y. If I had 3 arguments, I would put X, Y, Z, right? What should I say?
Oh,
X and Y. Okay? So that's one suggestion, right? And then you might want to do X to the power of, let's do Y to the power of X. Because the Y numbers are greater than the X's, and then they're going to, right? So is this going to work? So let's do a list here. So it's interesting that until you actually try to evaluate them, right? So we get an error. There's no Y, right? So there's only one argument, X. So then what should I have here? Right? Right? What's X going to be? A tuple, right? A pair. So this is going to work, right? But now, remember that I have the function power, POW, 2, 3, going to return 8. So instead of using the lambda, I would like to use power here. Well, I still have to use a lambda, but so I have a tuple here, T, and then I have a T now. Right? Can I do it? Can I do it in a shorter form? Yes. Right. So this is what I want to get. Right. So this would work. This will work as well. Unfortunately, I would want to use Yeah. Okay. Okay. Now there's a function called star map. Star map. So instead of using the star, okay, I can use star map. So I'm going to say just Paul. Okay. So instead of doing the lambda and saying the Pau star, right? So we work here. This would yield the same result. So the number is actually not that large. I thought it would be. Though we are raising to the power of 20, but yeah, 20 seems to be not that large, right? So instead of using the lambda with a star here, I can just use star map. Yes? They're here. Right? So instead of doing that, we can do star map. Okay? Yes. No, it's 1 to the power of 10, to the power of 20, 3 to the power of 30. Okay? So remember star map. It's star map and zip as a combination. They're extremely powerful. Okay? Yes. You see, you have a lambda t here. So we learned a lot about lambda a couple of weeks ago, right? Okay? All right. Let's talk about sets. Sets are very easy. So it's a collection enclosed in brackets. We can't really call it a sequence because the order is not important. The way the elements are mixed inside is randomly compared to how you provided them, right? So you provide them in this order. The way they're put inside is in such a way that they're efficient to store, and the order will be scrambled, right? It's a set. The order is not important. Right? Nevertheless, it is an iterable. Why? Because it's very useful to do something for every element. For instance, you want to map, right? It's very useful to map, to apply a map function, and for that you need an iterable. And whenever you turn a set into an iterable, the order will be completely random. So you have to remember that, right? It's very useful if you want to do one thing for each element. But if you want to expect if you're expecting a certain order, you're doing the wrong thing. Sets are very efficient in terms of storage, and they're very efficient in terms of checking whether an element is inside or not. Membership is very efficient, right? It's constant time, irrespective of the size of the set, right? So if checking that an element is inside the set takes the same amount of time, irrespective of whether the set has 1 million elements or 1 billion elements, right? It's a technique called hashing that there's no time for it here, but remember that. So if you want, there are also immutable, okay? Because you don't have a way of accessing an element. So in the list, you can go to element of rank 3. In a set at rank 3, you have no idea what you have, right? So they're also immutable. Being immutable is quite an advantage, though. We'll see soon when we talk about dictionaries. Now, you would expect that the empty set would be the empty brackets. But we also use the braces, the brackets, the braces, we also use them for dictionaries. And when you put them like this, there's no distinction between the empty set and the empty dictionary. And Python had to choose one. What would the empty brackets mean? And it chose that it would mean the empty dictionary. So the empty set is shown like this. Okay, order is not important, so this evaluates to true. Order is not important, so this evaluates to true. And notice the fact that if we write an element twice, Python will not get fooled. It's not an error, but it will keep only one copy of one inside. All the set operations are available, and it deviates from list and tuples, right? Because you put two lists together with plus. So here we put two sets together with the bar. So this is the set union, and intersection is the and sign, right? Because union and intersection are very similar to conjunction and disjunction in logic, and an or, right? And then it uses this sign. This is the typical or operator in most languages. This is the typical and operator in most languages. We also have set difference, with the meaning that you know, right? So remember, for set difference, we don't. It's not a case that all numbers in the second set should occur in the first, right? We can have 40 here. There's not an error. We still have a valid difference. We also have the symmetric difference. Remember the symmetric difference? So it's, if we have two sets, A minus B union B minus A. That's the symmetric difference. Okay? And it's essentially, yes? What do you mean subtract from each element? Uh-huh. Oh, so whatever occurs here will not occur in the result. Yeah. So it's set difference. Isn't that? Everybody knows what a set operations are, right? Who hasn't seen sets before? Actually, the wrong question to ask was nobody wants to be singled out. But okay, so symmetric difference, right? So here we have A minus B union, which I'm going to say as U, B minus A. This is also equal to A union B minus A intersection. Okay, so that's the symmetric difference. So it's all elements that do not, from both sets, that do not appear in both sets. All right, membership. So this evaluates. This is Boolean. Evaluates to true in this case. This evaluates to false. Remember, this is very efficient. And this is a subset test. So essentially saying that the set 1, 2 is smaller than the set 2, 3, 1. Because 1, 2 is included, it's a subset of 2, 3, 1. This is what we mean by smaller in the case of sets. 1, 4 is not smaller than 2, 3, 1. And if A is not smaller than B, it's not necessarily the case that B will be smaller than A. Right? We can have A not smaller than B and B not smaller than A. Right? Because they are they have a non-empty intersection, but they don't include each other. So hopefully all this is clear. All right. Sets of sets are also possible. We can create any collection of collections. Set of lists, set of tuples, tuples of sets, tuples of lists, anything you want. You can go multiple levels as well. All these functions work as expected, right? You can't quite say that what's the length of a set. It's more of a size of a set. But nevertheless, length is there and works for every iterator. So then it works for sets as well, right? Just for uniformity. And min, max, sum, yeah, they obviously make sense and therefore they work. Fine. Okay. Which function? The length? No, only the first level. Always the first level. Which the asterisk? What would you use the asterisk for? Oh, only the first level. Always only the first level, right? So it's especially because the sets can be, all collections can be heterogeneous, right? So for instance, this is legal, right? So how would I know? Yeah, let's say I go one level inside 2 and 3. Do I do that for? Do I try to do that for ABC as well? Right. So it's always one level. Okay. No, I mean not unless you write your own code. All right. So there's no predefined way. So let's write a function count distinct. Okay. Just for the sake of writing a function, there is a simpler solution. Right. I want to know how many distinct elements are there in an iterate. Right. So one way we can do it is start with the potential candidate result, which is the empty set initially, right? And then for every element in the iterator, we union it with the result, right? And at the end, we return the length. Okay? And the important trait of the set is that every element, if I add the same element multiple times, it will only be in the set just once, right? So this will automatically count unique elements. But I could get the same result by just saying len of set of sorry, it, right? If I have an iterate, so that would equally do. I take the iterator, I convert it into a set, right? The iterator itself is still the same, it hasn't changed, right? And then I take the size of that. Okay. Another interesting thing is to compute the transitive closure of a graph. All right. So let's say we have a friendship relationship, right? So 1 is friends with 2, and 2 is friends with 3, and then you have this saying that the friends of my friends are my friends, right? So then I would like to figure out that 1 and 3 are also friends. So I would like to expand this so that I get the transitive closure of the relation. So 1 is friends with 2, 2 is friends with 3, so then therefore 1 is friends with 3 as well. Right? And now you're going to say, oh, why is not 3 friends with 1? Right? We're not assuming that. So if I'm friends with you, you might not be friends with me. Okay? But we're assuming that it is a transitive. It is not a reflexive relationship, but it is transitive. So let's write a piece of code, and this is the last thing we do, that computes that does that. Okay? So here we learn an important thing. Oh, I think sets. I'm very sorry. Sets are actually no. They're immutable. They have to be immutable. All right, but let's learn one thing, which I think we touched on before, right? If I have a set, if I have a list, and we still have the list, right? I can produce a copy, right? Remember that? So I can say L3 equals L.copy, and then L3 is the same. If I change L, L3 has not changed, right? So it's very easy to produce a copy of an object, right? To keep it for later and change it in case it gets changed. So what are we going to do? We're going to keep adding to a set until the set cannot be changed anymore, right? So this is what transitive closure does, right? I'm going to try to find new potential pairs and add them to the set until I can't change the set anymore. At which point I know that I have added all the possible ones, right? Everything I appear to be discovering actually is already in the set. All right, so this is how the transitive closure works. I start with a result that is initially empty, right? And why is it S? This should be graph. All right. So while result is not equal to next, it's still different to next. It means that in the last round I have added some stuff. So I cannot be very sure that I can't add anymore. Only when in the last round I haven't added anything new, I can be sure that if I go another round, I will still not add anything new. So this is the time to finish and get out of here. Okay, so I'm going to take the result and make it a copy of what next is, right? And then for every pair in graph, and notice the fact that now, since we know what tuples are, I can write this. Our input is something like this, right? So then, when we write this kind of expression, 1 becomes the A and B becomes B, 2 becomes the B, right? So there's a matching between the two elements here and the two elements here, okay? So I'm going to take the AB in graph. I'm going to take the CD in the result. And then if B is equal to C, it means that A goes to B, which is equal to C. So B goes to D, meaning that A and D are actually friends, right? So then I can add A and D to my current working set, okay? So I will just go one round through the set. I will find all the pairs of pairs, right? See whether the last equals to the first, which means that the first of, so the last of the second is equal to the first of the last of the first is equal to the first of the second, right? And then the first of the first and the last of the last are friends, right? So I'm going to add them in. And if in the last round I haven't added anything new, then if I go again, I'm not going to add anything new, right? So it's time to stop. Clear? There is a simple program that computes the transitive closure. So for something like this, it will return something like this. And it works for any kind of elements. So if you want them to be strings, right, you can have them strings. Right? As long as you have a list of pairs inside. So this is another example, of actually a set of tuples, right? A set of pairs. So this is an example of collections inside collections. The input is the set of friendships, right? I have a set of friendships, but what is a friendship? Is a pair of friends, right? So I have a set of friendships, each friendship being a tuple of pairs. So then we need to do to generate all pairs of pairs, okay? All pairs of friendships, and see whether that friendship can be expanded. Because if they are together, the first of the first and the last of the last are friends. Yes? I didn't get a question. Which one? So this will go through the graph, right, and take all the elements from graph, one at a time. Now, graph contains pairs, right? So if it contains pairs, then A will match the first element of each pair, and B will match the second element of each pair, right? So as you go through something like this, right, A will be 1 and B will be 2. Then the next round, A will be 1 and B will be 3. And then in the next round, A will be 2 and B will be 3, right? Again, what do you mean by the default? What do you mean the first two? So Joe and John. And then I left out, okay. All right. So this A becomes Joe, this B becomes John, so then we get one print out. This print executes. Okay? Later, this A becomes Anne, and this B becomes Mary. Didn't get. Still puzzled? Still puzzled? Are okay with this? Remind me to go through this again next time. So homework is out. Is everybody okay with the homework for this week is out, right? So if you have any questions, email me.